Welcome to the video lecture on failure of classical mechanics. As a first step to understand the importance of quantum mechanics, presented by Dr. L. Cinderella, Professor and Head, Department of Chemistry, National Institute of Technology, Trichy. Classical mechanics is applicable to macroscopic molecules moving with velocity much lower than light. In this case, the energy transfer to the larger bodies, which we call as macroscopic molecules, gets transformed as translational energy. Translational energy, otherwise known as kinetic energy, makes the molecule or the body to move in some direction based on the direction of application of the energy. Whereas in the case of microscopic bodies, such as subatomic particles, transfer of energy is not only affecting their position, but also their momentum, due to their negligible space occupancy or size, and hence it always results in uncertainty with their position or uncertainty in their momentum. So when we attempt to measure the momentum of a small particle with 100% certainty, it tends to increase the uncertainty associated with the position of the body. This is otherwise known as uncertainty principle, proposed by Heisenberg. It is known as Heisenberg's uncertainty principle. Many of the experimental evidences have revealed that black body behaves as a vibrator, not associated with the translation energy as we have just now seen. See, in this case of a vibrator, when the energy gets emitted, it is not giving rise to a linear relationship, but it resembles a curve which is Gaussian in nature or typically a bell-shaped curve. This characteristics could not be explained by classical mechanics. In other words, this particular property of a black body is referred to as ultraviolet catastrophe, due to the reason, if it follows a linear relationship between the energy that is imparted to the body and the translation energy or kinetic energy associated with the body as a result of the impingement of the energy, then it would have resulted in a complete increase in the energy of the body with increase in the frequency of the incident beam, which did not happen. Hence, the energy transfer in the case of microscopic body is transformed not only as translational, but also as vibrational, rotational, and electronic energy also. Such excitation, which happens within the bound states of a body, because it is not making the body to get completely released from its bound state, it is not affecting the integrity of the body, it is only causing some changes either in the vibration or rotation or electronic energy of the molecule or body. This is possible only if there are some energy gap between the bound states between which the excitation of the body occurs. So this concept is known as quantization of energy, and hence the energy states are said to be quantized. Meaning of which is the energy value of each state is some discrete value and which remain fixed as a function of the number of state, as a function of the number known for that particular state. Then how the classical mechanics did not take a notice of such a quantization of energy? The early scientists missed the quantization concept only because of the fact that the quantization is in such low chunks of the order of E is equal to h nu, nu standing for the frequency of the radiation and h, which is Planck's constant. If you look at Planck's constant value, it is very, very low, 6.626 into 10 power minus 34 joule second. And the small value of this constant becomes insignificant in the case of macroscopic body, in the case of which every energy that is able to be noticed in causing some changes in the body when it is applied to the body would be of very high order than the small value of Planck's constant. That was the exact reason why this concept of quantization was missed in the early science. But in the case of microscopic bodies, which require a very high energy radiations, otherwise very high frequency radiation, matching with their dimension for the purpose of their characterization. So in this process of being impinged by high energy radiations, these particles are dislodged from their original position, thus affecting the momentum. Heisenberg's uncertainty principle is able to identify three pairs of conjugate variables which are complementary to one another. They are position and momentum, energy and time, time and frequency. Three sets of complementary variables which are conjugate to one another. If we attempt to measure position with 100% accuracy, then it would result in infinite uncertainty in its conjugate variable, namely momentum. The same could be said in the case of the other two sets of conjugate variables. As we understand quantum mechanics, it deals with the energy associated with any body in pockets of energy. Just to give a simpler example, which is able to show detectable amount of energy by way of radiation, we can refer to a black body. For that matter, any body would radiate as a function of the temperature of the body. The energy density radiated is directly proportional to the fourth power of its temperature, which is known as Stephen Boltzmann law. Q is directly proportional to the fourth power of temperature. And for each temperature of the body that is radiating, there is a particular wavelength at which the energy radiated is the maximum. Initially, we saw that the energy radiated fits into a bell-shaped curve or a Gaussian curve. So it is very easy to understand that a Gaussian curve has a maximum, and it is this maximum which is being referred to as lambda n. As per Wiertz displacement law, the product of the lambda max and temperature is always a constant, from which it is possible for us to understand that as temperature increases, lambda max occurs at a low wavelength. Similarly, as the temperature gets reduced, lambda max increases. The energy density of a black body radiation is being given by this expression as shown here, wherein if you look at, it has got two parameters on the right hand side, one a constant characteristic of the radiation, another one with an exponential factor, which shows a ratio of h nu to kT corresponding to that particular temperature, this taking up a value of a constant. Hence, the energy density of a black body could be given as the energy gap multiplied by the number of vibrators. Black body radiation provided the first and striking evidence for quantization principle by way of the exponential factor. It also provided evidence for the wave-particle duality of the microscopic particles by having the frequency in this expression. Frequency is a property associated with wave, whereas energy as in terms of pockets or bundles of energy is a characteristic of the particle. Hence, black body radiation provides the best evidence for the wave-particle duality of microscopic particles. Combining these two properties, namely wave and particle characteristic of subatomic particles, the properties that arise due to this duality are photoelectric effect, hydrogen atomic spectral lines, Compton effect, and Heisenberg's uncertainty principle. So we will see about them in detail in the other presentations.